This will be a short and optional mini lecture because all I'm going to do here is go through 3 problems of reactions that illustrate the directing nature of substituents. So let's figure these out. We've got an acetylated aniline that's getting brominated, chlorobenzene that we want to nitrate, and some kind of thiol that we're going to put an alkyl group on. So let's get started here with this acetylated aniline. All right. So when I look at this substituent, I see that, if that's my aromatic ring, I've got a nitrogen directly attached to the aromatic ring. So that means I've got a lone pair directly attached to the aromatic ring. So that says electron donating. But at the same time, I know that I can delocalize that lone pair of my nitrogen into the acetyl group as well. So that gives me this resonance contributor. Well, so that kind of makes it look like it's an electron withdrawing group. But generally speaking, as long as I can push those electrons into the aromatic ring, this is going to be an electron donating group. All right. Well, now what? How do I figure out where my bromine is going to end up in the aromatic ring? I'd say there's 2 different ways to approach this. The way we've looked at thus far is to look at the mechanism, always a good idea, and add our electrophile. So this is coordinated to our Lewis acid to make this a much better electrophile. We could even call it Br+. But in any case, that's going to give me an intermediate where if I put my positive charge here and look at the intermediate, I will be able to see that, yeah, sure enough, I'll be able to stabilize that carbocation by using the lone pair on my nitrogen. So this is a good thing. This is a stabilizing thing. This strongly implies that my acetamide substituent will be an ortho-para director. Okay, so that's one way of looking at it, looking at the stability of the carbocation intermediate. And that's absolutely correct. That's a perfect way to look at it. But I'm going to say there's another way to look at this from the get-go, and that is simply by looking at the electron density of your starting material in the first place. If I just look at the resonance contributors initially without even thinking about what I'm adding, well then it's pretty evident that I'm going to end up with a negative charge on each of the orthocarbons and on the paracarbon. And I'm obviously not showing all those resonance contributors. I can certainly show the next one. Oh, and I don't forget my positive charge here. Ooh. But all right, showing the next resonance contributor, boom. That gives me this guy. And then the third resonance contributor pops the negative charge right there. So by focusing on the starting material, I can also say this particular substituent is most nucleophilic at the ortho and para positions by just looking at those 3 resonance contributors we just drew up. So it doesn't matter how you figure it out. You can figure it out by focusing on the electron density in the starting material and saying, these are the most nucleophilic carbons. That's where my electrophile is going to be attracted. Or you can look at the stability of the intermediate carbocation. It truly is a kinetically controlled reaction where the most stable carbocation is formed, but you'll note that they both give you the same answer. Therefore, in this example, what we would expect to see is a mixture of both the ortho product and the para product. And like I've said before, it's an unfortunate reality that we cannot get one without the other. It won't be 50-50. We're going to have two ortho positions, so statistically it's more likely we'll have ortho, but sterically the para is favored, so you get a mixture. And of course, going back to chapter 1, we know that these two isomers are going to have completely different physical properties, so we should be able to separate them. I'm not going to say easily, but we should be able to separate them. All right, so that's example number 1. Example number 2, nitration of chlorobenzene. Now remember that chlorobenzene is the chlorine substituent, is the weirdo, one of the weirdos, the halogens, that deactivate the aromatic ring by the inductive effect, but are still ortho-para-directors. So we can go through the same illustration again. We know that, and I'm going to be really do some serious overkill here, but it's always good review. Got nitric acid and I've got sulfuric acid. And I know that ultimately a mixture of nitric acid and sulfuric acid leads to that nitronium ion intermediate. So that if I draw this guy up, then you should say, why would it protonate there? Well, it's going to protonate the negative charge, and it's going to deprotonate the negative charge. It's going to protonate here, there, and everywhere. Ultimately, we know from experimental outcomes, experimental data, that this is our active electrophile, and that's certainly the most straightforward mechanism for its formation. All right, so I have the NO2 electrophile. Then, if I just look at adding that powerful electrophile to my relatively weak nucleophile, now I'll look at the stability of the carbocation intermediates. My two choices would be to put my NO2 group here, with my carbocation there, or alternatively, carbocation here, NO2 group here. All right, now which one is going to give me the opportunity to use the lone pair on chlorine to stabilize that carbocation? Well, let's go through the bottom one. If I do this, I get positive charge here, and if I move this, I get positive charge here. Okay, I'm pretty much stuck. I never did manage to get a positive charge on the carbon bearing the chlorine. So none of these have the option of stabilizing the intermediate carbocation by resonance delocalization from the lone pair on chlorine. So that says this guy is one resonance contributor of the most stable carbocation intermediate, and therefore chlorine is indeed an ortho-para-director. And just to seal the deal, we will show the final step in the mechanism, which is, of course, analogous to an E1, where we just rip off that adjacent hydrogen and regenerate the aromatic ring. So there we go. Ortho-nitro And, of course, since ortho and para always accompany one another, we would also get the para product as well. All right, last example, we're going to look at this isopropyl thioether. And we're going to try and do a Friedel-Crafts with that. Okay, thioether is clearly, we've got some quite obvious lone pairs here, so this is clearly an electron donating substituent. So, based on what we've already seen, we should expect to see that our CH2, Cl, CH3 is coordinated to my aluminum trichloride. So we're starting to break this bond and we're starting to form this bond. So I got a big fat delta positive here. So that said, woohoo, let's take these pi electrons and react them with that growing carbon electrophile and just kick out that leaving group to make AlCl4. What does that give me? That gives me S isopropyl. I haven't done anything with those two double bonds. So let's see if I make my ethyl group go here. And it's a mess. ETH. All right, so that gives me this carbocation intermediate. So that's clearly a para substitution. Does that work for me? And yes, it most certainly does, because again, that leads directly to the stabilized carbocation. It's stabilized by that lovely octet stabilized sulfur cation. And so that makes this substituent an ortho-para-director. This is the expected outcome. So we should see yet another mixture of ortho and para products. So there you have it. Think mechanism, and it all becomes clear.